use the substitution x equals a secant theta to show that this integral is equal to this expression. When we're given a substitution, we should first find the derivative of the substitution so that we can easily substitute and remove dx from this integrand. A is a constant, so it remains as it is when differentiated. But the secant theta is actually a standard derivative found in the formula booklet. It's equal to secant theta tan theta. Also, don't forget to write d theta since we're differentiating. Since we're about to make a substitution into the integrand, we should find what the new limits for the integral are. We can do this by substituting a secant theta instead of x and equating them to each of the boundaries of the integral. This means we make a squared of 2 equal to a secant theta. Remember that secant theta is actually 1 over cosine theta, so theta would be pi over 4. The same goes for the upper limit as well. We're now ready to replace dx with our differentiated substitution, so a secant theta tan theta d theta, and x with a secant theta. This means we have to replace every instance of x with this substitution. We can distribute the cube and the square in the denominator. One of the secant thetas from the denominator can cancel with the one from the numerator, and we also cancel the a from the numerator and denominator. We can also factor a squared inside of the square root. Whenever you see a trigonometric function being squared, it might be helpful to look to see if this can be represented in a Pythagorean identity. For example, secant squared theta minus 1 can actually be written as tan squared theta. The a squared and tan squared underneath the square root become a and tan theta. The tan in the denominator then cancels out with the tan in the numerator. Secant squared theta can be written as 1 over cosine squared theta, so it can just be written in the numerator. In the end, we get cosine squared theta over a cubed. Although we have already simplified it very much, we still cannot easily find the integral of cosine squared theta. For this, we can pull up the double angle identities from the formula booklet. We will locate an identity that involves cosine squared theta. For example, 2 cosine squared theta minus 1. We can then rearrange this equation of cosine 2 theta equals 2 cosine squared theta minus 1 to just isolate cosine squared theta. So we get cosine 2 theta plus 1 over 2. We can then substitute this expression into cosine squared theta. This is useful because cosine 2 theta is a double angle which is significantly easier to integrate than a square. 1 over 2a cubed is a constant that can be taken out of the integral. To integrate cosine 2 theta, we can start with a derivative and an integral we already know. For example, sine theta differentiated is cosine theta. What about if we take the derivative of sine 2 theta? Using the chain rule, we get 2 cosine 2 theta. We can now divide both sides by 2, and we get cosine 2 theta equals the derivative of sine 2 theta over 2. We can integrate both sides, and we found the integral for cosine 2 theta. So now we can use the fundamental theorem of calculus and substitute the upper boundary into theta, and then subtract the lower boundary when substituted into theta. We can combine the fractions by making the denominator equal to 12. And then take out the 12 out of the parentheses. So we get 1 over 24a cubed, 3 squared of 3 plus pi minus 6. So that's it for this video. Thank you for watching. I hope I helped you with this question. Please like and subscribe. Bye!